Hi guys, good morning. Welcome back to the new video. Sorry, I'm a bit late. The reasons are, but yeah, before that, this is one of the kind of problems we have never seen in the last 3-4 months. Why I say that? Because firstly, I'm gonna say what's gonna be applied in this. But yeah, if you want to know the entire intuition, please skip the next 5-10 seconds, and that would be great. So we're gonna see greedy plus DP being applied in a problem. That's one of the greatest. You know DP, you know greedy, but yeah, that's one right. Cool. Let's start the problem itself. Make array strictly increasing given to string to integer arrays called as array 1 and array 2. Cool. Return the minimum of operations, possibly 0. Needed to make array 1. See, array 1 have to be make as strictly increasing. Cool. What's operation like? Operation is that we can choose any index, okay, I, and any index j, and then we can assign ARR of I, because for sure we have to make ARR of 1 as increasing, right? So we have to assign some values to ARR of 1. So ARR of 1 will be assigned some values which will be equal to ARR of 2 of j. Cool. And if there is no possible way to make it increasing, then we will return a -1. So for sure, as soon as we read the problem itself, nothing came in the mind, no worries. Now we will see the example. From the example itself, slowly we try to build the intuition itself, right? If not, let's say if you are at an interview, so you build your example by yourself, and from building example by yourself, you try to build the intuition by yourself. In this case, we have examples, so we will build the intuition from the example itself. And that's not important that okay, all example cover every intuition possible. We have to maybe think slight out of the box to think of bigger, better examples also to bring out more stuff. But cool. If we look at the first example, we have 1, 5, 3, 6, 7. So it's like okay, 1, 5 increasing, okay, then it decreased and then again increasing. So if I clearly look, okay, 1, 3, 6, 7, it would have been if 5 would have not been there. So 1, 3, 6, 7, it's increasing. Just this 5 came in picture, which made my equation wrong. So what I could do is, okay, replace 5 with something which is between 1 and 3. I will go and find something which is more than 1 in my array ARR2. And okay, I will just get, okay, more than 1 is not, okay, more than 1, oh, I have 2. More than 1, I have 2, and that more than 1, because just more than 1, it's 2, and that 2, it is less than 3. For sure. Now I can make an array 1, 2, 3, 6, and 7, and now it is strictly increasing. So while reading the example itself, one thing I got to know, okay, I could see that my 5 was making an issue. So I went to look for some element in ARR2 which is between 1 and 3 for sure, because the 5 was making an issue. So I want to replace 5. Replace 5 with some number such that it will be increasing. For that, any number which is between 1 and 3. For that, okay, number which is just more than 1. So I can place after 1. And that just more than 1, if I place it here, then it should be also less than equal to 3. Because after 1, okay, after 1, it is the just higher number. Before that, any smaller number possible. For 3, it can only be this. Thus, I could infer one thing from the first example itself. Okay. To replace any element in ARR1, what I can do is I can go, okay, I know it is my previous element. I need to replace my element, let's say 5. I'll go and search for any number which is bigger than, just bigger than 1. I'll get, let's say 2. And I'll replace this number by 2. And now I will just check, okay, after replacing this number by 2, is it still making my equation higher, which means is it still less than 3? If it is, I'm good. If it is not, sorry, I cannot replace, which means if it would have been 5 and let's say that the number 2 would not have been there at all, so you could not place after 1, the next high number would have been 3, so you would have placed a 3 here. But then as soon as you place a 3 here, the next number coming in, it is 3, and we know it needs to be strictly increasing. So again, we have to replace this number by something else, which is just more than 3. So I will have replaced by 4. And that's how one thing from example 1 we can infer is to replace a number. How to choose what to replace? I'll just go and quickly say, okay, to replace my number 5, I'll go and see any number in my array 2 which is more than equal, like which is more than 1, not equal to, more than 1. I'll go and quickly say, okay, more than one, just more than one, place it, and just see, okay, if that number is less than my next number. If it is, good. If it is not, okay, I'll just try to replace my next number then. But yeah, I am trying my best. That is, trying your best is the greedy one. I choose the greedily smallest number possible to replace this number. Okay. From the first example, we got to know some information that, okay, I'll just try to replace. When I am set to replace a number, I'll try to replace with the next higher number. Just next higher number. And that's it. Cool. As we go to the next example, it is 1, 5, 3, 6, and 7. I could again see it's the same example. So firstly, I will just try to replace my number. Okay. Maybe it's possible, maybe not. It's not required to replace the number at all. Maybe it would have been 1, 5, 8. Oh, sorry. 1, 5, 6, 7, 8. Then it's not required to replace the number at all, right? But still, I'm still here trying to replace a number. Why is that case, Aryan? I'm not saying it's not compulsory to replace a number. You can skip also. So as soon as you read this question, you saw, okay, 1, 5, it was increasing. Then the number came as 3. What if the number would have been still bigger? I would have replaced it or not. Which means I have an option right now. I can either replace it or I cannot. That's where, when you say these two words, either I can replace it or I cannot. So the first thing which comes in your mind is a recursion. And as we have seen, knapsack, take it, not take it, replace it, not replace it, have it, not have it, DP also comes in the picture. Like it is, while reading the problem itself, while speaking in English, we say, okay, replace it or not. Option we have two options, to replace it or not. That's the reason, okay, maybe it is some case where DP or recursion is being applied and then we can apply DP or something, because we have heard of these kind of statements, okay, replace it or not replace it. It is another intuition that, okay, DP can be applied here. Now, as we see this problem 5, okay, although I have 1, 5, I will try to replace it with the next higher number. After 1, the next higher number is 3. I will replace it by 3. Okay, cool. I replace it by 3. Now, as I reach the next number, which is 3. 3 here, it is equal to 3. I want it increasing. So I have to replace the next 3 also with something. I will replace it with the next higher number. After 3, which means my previous number was 3 now. See, my previous number is 3 now. Oh, I am moving in my array. I have a number, I am at index I, but I also need to keep track of what was my previous number, because my previous number can get changed if I am doing an operation. If I am skipping that, no worries at all. But if I am doing an operation, my previous number can get changed. So one other intuition which came to my mind is, it is just simply we are speaking out. While speaking out, some words are coming in. That words are actually the intuition. As I am going in, oh, my previous number, it can get changed. So for sure, I also need to keep track of my previous number. And also as I'm going in my array itself, so maybe I can have also an I. See, it is now, I'm just thinking, it is not sure, okay, it will be the final state itself. It can be possible that you can think of many states of DP, I, J, previous, another thing also. Then maybe you can try to make it compact, try to bring in your complexity, all that stuff. So yeah, right now I'm just thinking, okay, as I'm moving on, so I know, okay, the index I'm moving on, but at an index, if I am at here, I also need to make sure what was the previous value I placed in. I know the previous value placed in was a 3. So for sure, 3 here, previous is 3. I need to change my current number because 3, it can't be here. So I'll just go and see, okay, hey, in array 2, what is the next higher number more than 3? It is 4. So now to easily find out, see, one operation was to know the next higher number, If here in this case, I want, okay, what is the next bigger number than 1? So I need to find that as fast as possible. So for that, simply, if we want to find any higher number, upper bound for that, you want to sort the array. For that reason, I will simply sort my array 2, just so that I can find the next higher number. so that I can find the next higher number. I will just sort this also, 1, 3, 4, so that I can find the next higher number more than 3. I will get 4. I will replace this number by 4. And thus, you will see, as soon as I am applying a replace operation, my operation is being increased. Earlier, I replaced my number 5 by 3, one operation. Again, I increase my 3 by 4, other operation. So in total operations were 2. Now I move on to the next number. Okay, it's 6. No worries. It's more than, but still, it is, I said, no worries. No worries. Here also, my number 5 was more than my 1. Still, it was no worries. But still, I replaced it. Why? Because maybe for the next number, it is the previous number and it would have been smaller. So at every point of time, I'm thinking, okay, I have 2 options. I can replace it, I cannot. Maybe I can just skip this and I can move on next. Then I have to make this 3 more than equal to 5. More than 5. Or I can just replace it, make it to the smallest possible number, which is more than 1. It is 2. Then the previous will become as 2. And then I will go on to the next number. That's how we know, okay, I need to keep track, okay, as I'm moving on in the array, I need to keep track, okay, I need to have a I. I need to also keep track of the previous number, and that number I can change. It is on my chance, okay, I want to change or not. If I want to change, good. If I don't want to change, good. Now, as we look at this, see, as we're reading this, ultimately we're thinking of multiple things, and that thinking part I spoke entirely. So what we think ultimately was, if we are at a number, we have 2 options. Either we will take it, when I say take it, I mean replace it with a next smaller number, next higher number, which means we know the previous number, it is 1. I'll replace this number with the next higher number, which means I'll go and search for this previous number in my array 2. For that, I need to sort my array 2. I will sort it initially. I'll go and find, okay, what is the next higher number? It is 3. I'll replace this number 5 with the number 3. It is one option I have, which means replace it. Else, other option is leave it. See, usually we say, okay, take it, leave it. When I say take it, it means replace it. When I say leave it, it means move on, which is hard for you, I know. But yeah, you have to move on. Cool. Now, what we will do is, okay, we have this number 5. Let's say I just moved on. Moved on to the next number, which is 3. Now, my previous now is 5. Now, my task will be, as 3 is smaller than 5, so I cannot move on now. Now it will be hard to move on. I know it's hard for you, but yeah, I can do one thing. I can still do a replace operation. I can still try to make this number more than my 5. I'll go and search. I can. Yeah, I can. I'll just make this number 3 replace with a number which is more than equal to 5. I'll land at 6. I'll replace it. It will become a 6. Now I will just have replaced a number. I will just move on next. Then I'll just keep on going. So you know now at every index, you have 2 options, either replace it or move on. To replace it, you need to have the previous also. You need to know the information of previous also. For that previous information, what you will do is, you will keep track of the previous change you did. What is the previous element you had? And that is all the simply how to do this problem. Cool. Let's quickly do a recap. What we did is this, that we have an option of replace it or move on. Replace it, which means for that I have to go on to the next higher number. For this, next higher number is 2. I'll just simply replace it with 2, and then I can simply go on. And please keep track of your previous number, because you know you are at I, but you also need to know what was your previous number which you had, or if you changed, what is the previous number after you changed it. Cool. And that is what you have to do. Now we know we have the recursion. We know how the recursion is looking like. We know what we have to do. We know that, okay, we have 2 options. We know what are the recursion parameters. How we saw while iterating, by speaking in English, that okay, it was I want, and also I need to know the previous information, because I'm changing my previous, and at every time I also need to know my previous information. So I know the recursion parameters are, as I'm simply moving on, no matter what, I need to know the index. As I'm simply moving on, and also as I'm replacing a number, so I also need to know the smallest possible number which I replaced, which is the previous number I know. So that is the reason I need to store a previous number also. Now, can it work in my time complexity and stuff? Can it? I have previous. Now my DP state, ultimately, because so now I know it's a recursion, but for sure, as soon as the question comes in, take it, not take it. And for sure, if you're still, if it's your first question from us, and you have not watched the complete TP problem solving playlist, in that I have shown you entire recursion trees, entire, like, properly showing, okay, what is the sub problem like. And this is a very common problem we have covered 8-9 times in this playlist itself, that okay, take it, not take it, take it, not take it, have it, not have it, replace it, not replace it. So if you are confused on, okay, how the problem is a repeating sub problem and all that stuff, please go and watch this. And for that, entirely everything we have made playlist for every part, so please go and utilize this part, especially this 150 problem set. Although we have the Aryan TSA playlist, but still this 150 problem set I only update this particular playlist when I see some problem which is awesome, like legit a combination is amazing. If it applies something which is very unique, something which can help you in every problem, only then I add in this particular place. So please make sure that you utilize these particular playlists very well. Now, as we know for sure, we have your I, we have our previous. Firstly, if you are still not sure, okay, how the recursion tree is being built, as simple as that. If I am on I know what is my previous state. I can have two options, keep it and replace it. As I keep it, which means I will keep this particular number, I will go on to the next number. Next number, as I go on, then the index will become next index. Next number is 3. Previous number will get updated to the last number. It is 5. Now, again, I have two options: keep it, replace it. If I want to keep it, it should be the number 3 should be more than 5, but it is not the case. So that number is less, so I can't keep it. I need to have an increasing array. So the keep it option is not for me. To replace it, I have to replace it with a number more than 5. More than 5 I have to replace. For that, I need to have a number more than 5 in my array too, but it is also not the case. So replace it will also not work. Now, if I did a replace it on the initial step at I equal to 1, then what will happen is replace this number with the next higher number. Next higher number was, for 1 was 2. So I'll simply replace by 2. Again, as I move to the next index, I have again two options, keep it or replace it. I can keep it because 3 is more than 2. I can keep it, good. To replace it, simply go and find next higher number more than 2. It is simply a 3. So I replace 3 by 3 itself, although I'm just trying every possible way, right? And that's how you can simply go and trying to build a recursion tree. And for sure, it has a repeating subproblem, because just imagine your I and your previous comes same at any step on point of time. So for sure, it can happen that the recursion tree builds in and you have the repeating subproblem. If you're still confused, Aryan, how you can say that it has a repeating subproblem, again, please go and watch this. We have covered this entire 8-9 times in this entire playlist. We have seen many problems like that, and we have saw the complete intuition. It's very long to build this particular tree. That's the reason I could not build it entirely here, and it would also make it long. So that's the reason. But yeah, now you know you want your I and your previous as your DP states. So firstly, will it work? Yeah, it will. I is up till a 2k. Your previous is nothing but numbers. Your previous is nothing but a numbers of what? Array 2. Your array 2, it can have at max what numbers? At max m numbers. If your array 1 has size n, array 2 has size m, so your array 2 can have at max m numbers. So your previous, it can have at max m distinct values. So basically, previous will have m distinct values, which is also at max 2k. So your complexity, it can be I, which is 2k, and also previous, which can have at max m distinct values. It can also be at max 2k. So 2k, 2 into 2k, which is around 4 into 6, that will simply work for you. So for sure, you can apply your DP with these two states. That's the reason how you know that you can apply your DP here. Now, as we come back to the code, for sure we have done everything. Now, if we just simply see the code, first, as we saw that we need to apply a binary search kind of stuff on my array 2. For that, I need to sort my array 2 down. So I simply sorted my array 2 down, right? Now I took here, although I took a map of my DP, right? Which means a map of pairs. Now, as you know, the DP state is I comma previous. Your DP state is I comma previous. So for that, you know, the previous number, it can go up till 1e9, right? Okay, but it can have at max m distinct values. So for sure, your previous part, this previous part, either you can hash it out, either you can have a DP of a 2D vector, but this vector at max, its value, it can at max go to 1e9. So you can't initialize such a big vector as such. So you have to make it, maybe hash it out all the distinct values to a simple integer values up till m size, or other thing you can do is simply take a map which will actually say, okay, I to previous, it is the value, I to previous, it is a value. Now you know how this is another amazing concept you learned, that okay, you have simple thing, although you know that your previous, it can have m distinct values, but you need to store in your DP. Since so far you have been studying, okay, I will store a 2D array and will have a DP and previous. Here if you just make your DP and previous, so what will you make is a DP of size 2000 and a size of 1e9. That is not at all possible. So basically, you know that here it can have at max m distinct values. So please hash those m values in the range of 2000. So you can easily hash those m values in the range 2000. By that, if the value is even 7e8, still you can map it to any value inside this range. So if you don't want to get into the jhanjat of hashing and putting these values, simply go and use a map. Now you will say, Aryan, because of using this map, my complexity will increase by log n. Yeah, it can. But if you want the solution of that also, so you can use a vector of unordered map. Because simply you know that, okay, your I will always remain in the range. It's just the reason that, okay, your previous, it can be in 1e9. So if you use an unordered map, what will happen is your vector will initialize with the range of 2000, which means the n, and then with your DP of I, then you have, okay, another kind of a map which will have previous to its value. It is previous and it is the value. When I say value, which means DP of I previous is having this value. That is how you can also use this particular stuff, okay, to reduce your complexity a little bit. But ultimately it will not help us much, although it can decrease your runtime a bit, but complexity wise it will still remain same, because the extra log n factor or log m factor, it's being added. I'll show above, but yeah, it will not affect you that much. But yeah, if you still want to optimize it, you can use a simple vector of unordered map of DP. Cool. Now it is one options which you can have. Now in this, I specifically stress on this point because in this your hashing part also comes in picture. The interviewer can ask you, hey, why are you using this? Why not a simply 2D array? Because you know the previous value can have a bigger size. So either you have to hash entire array to down to actually the values inside the range of 2000, or simply use a map, because map, it can just store unique values by itself. Now ultimately I'll just quickly go on and find the answer by simply using a recursive function. Let's say name it as help. In that you simply pass your DP array. You simply have to know your previous, your current index, and also array 1 and array 2 for your values. Array 1 to know, okay, what is the current value of ARR of I, and array 2 to find, okay, to what value I replace it, such that, okay, it should be more than my previous value. Cool. And ultimately, as I return my answer, although I'll go on to how the recursion is working, but yeah, as I return my answer, ultimately I will know, okay, if my answer is more than int max by 2. Please make sure I didn't take it int max, I took int max by 2. Why? I will show. But yeah, my maximum was not int max, my maximum was int max by 2. If it is more than equal to my int max by 2, then my answer is -1, because the answer is not possible, it's int max. I want the minimum answer possible. If it is, okay, I have answer. I will again repeating, I will show you why it is int max by 2 and not int max. Cool. Let's quickly go to recursion. Now, so recursion as simple as that. We have a base condition, we have a recursive function, and we have the return. Cool. As we have the base condition, as we are simply trading on array 1, I'll simply say, okay, if my I reaches the end of array 1, I am good, I am done. Simply return 0, which is okay, you are good, you are done, no possible ways left, and that is your answer. Now a simple memorization check. If you have seen the same state of DP of I comma previous, then please, if you have found that state already, please return that state back. We don't want to repeat our state because we are using a DP. We are using a memoization. So please utilize that memoization. I will simply go and find, as it's my map, so I'll simply go and find if I have found this DP of I comma previous. Okay, please, you are good. Please return that DP of I comma previous. Now, our base case is done, our memorization is done. Now you will see that I initialized my answer with int max by 2 and not int max. Why, you will say? It is because you are returning your help, which is simply your recursive function. Your recursive function is returning your answer, right? Your answer in worst case can be if it is int max. If it would have been an int max, so your answer in worst case it would have been int max. If the answer would have been int max in worst case, then int max plus 1 would have overflown, and that overflow in C++ goes to a minimum number. So you are taking minimum. Overflow will actually make your answer wrong. That's the reason that it should not overflow. I took as int max by 2. So that even if it is int max by 2, even if I do a plus 1, still it will never overflow, and still I'll get my answer. Thus, I took my answer as int max by 2. Although you can take a long and all that stuff, but please make sure that you have to also make sure that, see, it has such amazing concept. You saw greedy, you saw DP, you saw hashing, you saw overflowing. Can you just imagine the interesting part about this problem? Like how much things you are learning this problem. That's amazing. Cool. Now, as I have my answer, I know one thing. Either I can take it or I can, which means either I can replace it or I can leave it. If I have to replace it, I need to know what is the next higher number which is more than my previous number. So I will go and search in my array 2 for the next higher number more. See, next higher which means upper bound number more than my previous number. Now it will just give me a pointer. This upper bound gives me a pointer, and I want the index itself. So I will just simply subtract it with array2.begin to get the actual index and not the pointer. Now I have the index of the next higher element more than my previous element. Now I have two options. Either I can move on, which means let's move on. Although it's hard for you in your real life, but yeah, you have to move on here because it's easy. Simply moving on. But yeah, please remember, to move on, your current element should be more than your previous. Only then you can move on. It's also not easy in this case. Yeah, you can move on when your current element, because for sure you want it increasing, right? So your current element, it should be more than your previous. Only then you can move on to next. If it is the case, then simply grab, okay, answer. You are simply updating your answer with the minimum answer. Helper is the next helper function. For the next previous value, for the next I plus 1, because you are going on to I plus 1. So for I plus 1, the previous value will be array 1 of I, because you have not replaced that. You have not replaced that. So it will still remain array 1 of I. And you will simply go on and write it as it is, because it's not much required. By this array 1 of I, if it is more than your previous, then you simply go on to the next element, which is I plus 1, and your previous will become array 1 of I. But if you try to replace it, and you know that you can replace it with this ID. But Aryan, what if this ID is itself more than your array 2? Which means, as you saw here, you were trying to replace it. You were trying to replace this number 3, but it was being replaced with more than 5. More than 5 I was not even having. So my ID will point at the end, which means more than my array2.size. If it is more than, I can't. So I can only do if it is less than my array2.size. Right? As it is less than my array2.size, which means, okay, I have a valid number, valid index inside my array2. Then I can simply do, okay, now I know what is the valid number I have to replace with. I have to replace with array2 of ID now, because the number has been replaced, and simply going on to the next number. As simple as that. These two are the options which we have to consider and update our answer with the minimum possible answer. And then ultimately I have my minimum answer possible, and I can return in my DP state by simple memoization step. So you know memoization step, how it works: a simple here memoization, a simple here memoization, and a simple initialization. That is how you can simply solve your problem. Now you have simply done. Let's come to the complexity part. Complexity very simple. How? Firstly, you are moving on the n elements. So for sure, n, because it's a recursive condition, because we know we have applied a DP. So for sure, that state will actually go to at max n times. Previous, as I showed you, previous value, it can be pretty large because it's a number. But actually, it is a number of array 2. Array 2, it can have at max m numbers, and which means m distinct numbers. So for sure, your array 2, it can have, your previous can have m distinct values. So basically, your previous can go at max m states. Cool. Your recursion is going m into n. But you also have your finding of binary search inside your recursive function. Your binary search is being done on array 2 of size m. So it is a log m extra part which is being done. But you will also say, Aryan, you used a DP, you used a map. So for sure, that map factor also comes in picture. Yeah, it will come in picture. You will assign, it will come in picture. You will find it, it will come in picture. So it comes in picture and do a log of n. But yeah, you saw that, okay, for m into n DP state, both of these will be added as such. So it is nothing but O of m into n log m plus O of m into n log n. Although you can just also ignore this part because I showed you what optimization you can do, and simply, even if you don't ignore, still the complexity wise it is nothing much affected. So ultimately you can say your complexity will be O of m into n log m. Right now, exactly in this case is plus m into n into log n2, but it is plus, not multiplication. But yeah, still this plus also increases complexity a little bit. But yeah, that is how you can make your code a bit clean. If I would have used the one I showed you, which is an vector of unordered map of a DP, unordered map of DP, then it would have made a code a little bigger and more if conditions. So yeah, that's the reason I just took it. But yeah, ultimately it will be something like this: O of m into n into log m. And space is nothing but O of m into n, because you're simply using the DP of states, basically m into n states. That's how you can simply solve this problem. I hope that you guys liked it. If yes, then please do smash the like button. In this, you learned a lot of things, greedy, DP, hashing, and doing all that stuff. I hope that you guys liked it. So, take care. Bye.